Hello everyone, welcome to this session. My name is Swi Innocent and I'm taking this course Elements of Database on behalf of Dr Lienou JP. I've already sent the notes to you, so today we shall be looking at lecture 1 in part 1. So if you open your notes and follow up, or you can just follow up, this video is going to be good. Without much ado, let us dive directly to the heart of the matter. So in this course we shall talk on database system, data models, database design, SQL, transaction, concurrency, administration, and then we'll do some practicals. I'm going to explain more on how we go about with the practicals subsequently. Now, why do we study databases? First of all, many applications nowadays contain a large amount of information, and this large amount of information will be better managed with databases. Again, database systems give us a set of tools for storing, searching, and managing information. In computer science, databases are a core topic. Basic concepts and skills with database systems are assumed that you already contain at your graduation. Now, what is a database? A database is a set of information held in a computer. That's what the Oxford Dictionary defines. Free online dictionary of computing defines a database as one or more large structured sets of persistent data, usually associated with software to update and query the data. While dictionary.com defines a database as a collection of data arranged for ease and speed to search and retrieve. Some examples of databases involve web indexes, library catalogs, medical record, bank records, stock control personnel systems, product catalog, telephone directories, and so on. There are so many of them. You can name them. Now, a database system consists of four main elements. The first one is data, which is the database itself. Then the software that we install that will help in the management of the database, the hardware in which we install the software, and finally the users, the people who use the software to gain access to the database. But we shall focus mainly on the software. Softwares like when we talk of software here, we're talking of the database management systems. It could be Oracle. We'll just look at it. We'll look at this after this. But these database management systems help us to store, update, retrieve, and organize our data. It also helps us in the protection of our data. Database users. We have several users involved at the database. We have the end users. The end users they use the database to achieve some goals. We also have application developers. They write software that allow end users to interface with the database system. Database administrators, they design and manage the database systems. Then database system programmer, they write the database software itself. Database management systems. A database is a collection of information. While a database management system is a software that controls that information. Examples of database management system, that is software that can help us to control information, include Oracle, DB2, created by IBM, Microsoft SQL Server, Microsoft Access, Ingress, PostgreSQL, MySQL. We also have other DBMSs like XAMPP and WAMP. They are common. I'm very sure. In this course, we are going to use XAMPP during our practicals. So make sure you install XAMPP because we're going to be needing it subsequently. What does databases? What does DBMS does? What the DBMS does? First, it provides the user with three languages: data definition language, data manipulation language, data control language, which we should subsequently look detailedly what each of those languages stand for and what they do. Uh, these languages they are often the same languages. They perform the same function. So database management systems provide what we know as persistence, concurrency, integrity, security, and data independence. Uh, they also give us the ability to have a data dictionary. The data dictionary describes the database itself. Now let's look detailedly what a data dictionary is. The data dictionary or catalog stores information about the database itself. The data about the data, that is data about the data, or we can just call it the metadata. We can call it the metadata. Almost every aspect of the database management system uses a dictionary. That's because it is the foundation of database management system, and this dictionary holds descriptions about uh, database objects like tables, users, rows, views, indexes. It also contains information which we use as with the data. That's data logs, and it has schemas and mappings. There are several types of database systems. We have number one could be the file-based system. The file-based system stores data in files. Each of these files have a specific format, and that is how you get to access it. Programs use these files depending on knowledge of that format that each of the files have, right? Some of the problems with file-based systems is that it has no standards. There is data duplication, data dependence, and there is no way to generate ad hoc queries. Then no provision is equally provided for security, recovery, and concurrency, which brings us because of this backdrop, we now move now to the other type of database system which resolves most of this problem, called the relational database system. But you have to note that before the 1970s, this relational system had a lot of problems because to navigate between queries required complex programs, and there was minimal data dependence with no theoretical foundation. But in the 1970s, E.F. Cort wrote a relational model for data for large shared data banks, and introduced the relational model. The relational model, now we now know that it contains information, and the information is stored as tuples or records. Tuples or records. Some people will call it rows, right? So tuples or record or rows, and they are stored in relations or tables, right? A table containing rows, that table is called a relation, and then the rows, they are called what? Tuples. uh, there is a sound mathematical theory of the relations now, thanks to E.F. Codrock. Most of the database management system are based on the relational based model, and this model covers three main areas. We have the data structure, data integrity, and data manipulation. We shall look more details in the next lecture. ANSI Spark architecture. First of all, what is the meaning of ANSI? It means American National Standard Institute, SPARC, Standard Planning and Requirement Committee. This was proposed in 1975 for databases. This three-level architecture contains three main component. We have the internal level, conceptual level, and the external level. The internal level is for system designers because it focuses on the structure of records on the disks like files, pages, blocks. It equally focuses on indexes and ordering of record. It is used by database system programmers. Example of an internal schema, we could have record employee length 44. You actually see that it describes the length of the record on the hard disk file, and it equally provides more details that the database programmer will be able to understand. Conceptual level. It deals with the organization of data as a whole. It provides an abstraction for the user, and it hides some unnecessary details of the internal level. This level is used by database administrators, DBAs, and application programmers. An example of a conceptual schema, we could have, a create table employee, and we'll put the details, name, which takes a varchar of learn 25, salary of type real, department, which is a varchar of learn 10, and so on. External level. The external level provides the database tailored view to the user. Parts of the data may be hidden because it is presented in the useful form, and it will definitely hide unnecessary details from the user. We have an external schema. You have payroll, which is a string. Now payroll is a payroll, and in payroll we have a name, which is a string, and each person in the payroll will have a salary, which is of type double. We equally have personnel, and the personnel will have a name, and the personnel equally belong to a department. So that's how it looks. Excuse me. Great. Okay, well, online. Next, mappings. Mappings translate information from one level to the next. We could have a mapping such as external conceptual mapping, conceptual internal mapping. We shall look at it just briefly. These mappings provide what we know as data independence, and data independence comes here in two levels. We have the physical data independence and the logical data independence. Physical data independence changes the internal level. It makes sure that changes made to the internal level don't affect changes at the conceptual level. Logical data independent, on the other hand, ensures that changes at the conceptual level should not affect changes at the external level. Now, take a look at this diagram. On the right hand side, we have on the right hand side, excuse. On the right hand side, we have a data that contains we have a diagram that starts from let's start from the bottom. That actually the bottom will describe the physical layer where data is stored. Then it moves to the relation. This relation is what we call the conceptual internal mapping, because it links the conceptual level to the physical level. At the conceptual view, that is where we know that the users are what the database administrators. Then it is mapped to the external view. The external view, the mapping is called what? External conceptual mapping, because it maps the conceptual view, the external view to the conceptual view, right? Then we know that the external view provides a well-tailored data user interface to the user. Next class, you should do this assignment. Make sure you do this assignment before next class. And then in the next lecture, we shall talk on relational model, relational data structure, data integrity, data manipulation. For more information, you can just read lecture 2, which is coming up very shortly. If you have any questions, you could write them in the comment section below, or you could just write them in our WhatsApp group chat. I'll respond to them at the earliest. Hello everyone, once again welcome to this session. My name is Swi Innocent Chair, and I'm taking this course Elements of Database on behalf of Dr Lienou JP. Without much ado, let us go to lecture 2. Relations and relational algebra. In this lecture, we shall talk about the relational model, where we'll talk specifically on relational data structure and relational data manipulation. Without much ado, let us start. Relations. A relation is a table. We use tables to represent relations. For example, a relation between people and email addresses. You see here that in the first column we have names of people, Anne, Bob, and Chris, and in the second column we have email addresses. Mathematically, a relation is a set of pairs. In a given, let us use our example. Anne and the email address. We can write out a set of pairs just as we've written here. Anne, comma, the email address. The second row, Bob, comma, the email address, and so on. Each value in the first column is a name, and each value is in the second column is an email address. So in general, we say we can call a column a domain. A domain means that all the elements inside the domain are similar, and all the elements in this domain are similar. This is the domain of names, and this is the domain of email addresses. A mathematical relation is a set of tuples, or we can call it a sequence of values where each tuple corresponds to a row. That means that a row can also be called a tuple. So these are tuples. In other terminologies, we will see things like degree of a relation and cardinality of a relation. A degree of a relation describes how long the tuples are, or how many columns are present in the relation. If we take an example of this relation here, this relation which you have here, we will notice that we have 1, column 2, column 3. So the degree of this relation is 3. 1 column, 2 column, the third column. We have 3 columns there. The cardinality of our relation, it describes the number of tuples present in the relation. Now let's use the same relation as our example. We'll see that we have how many tuples or how many rows? 1, 2, and 3. We have three tuples, meaning the cardinality of this relation is equally 3. Mathematically, we can define a relation R of degree n where values comes from domain A1 to A2 as a relation R is we say that the relation R is a subset of the domains A1 of the Cartesian product of the domains A1, A2 right up to AN. Cartesian product of domains A1, A2 right up to AN can be defined as the set A1, A2 to AN such that A1 belongs to the domain A1, A2 belongs to the domain A2, right, and AN belongs to the domain AN. Relational model. Data manipulation. Data is represented as relation. Manipulation of this data is done using query and update relation, which corresponds to the operations of the relation. Relational algebra describes this operation. They take relations as argument and produce a new relation. It means that you take a relation, you perform operations on it, and the result is equally another relation. you think of numbers corresponding to operators. When we are dealing with numbers, we use operators like plus, minus, division. Or when we are dealing with Boolean variables, we use operations like and, or not. But when we come to relational algebra, we use two kinds of operations. We use the common set theoretic ones and the operator specific relations. For example, projecting one column of the other. We shall look at this projection subsequently. Very soon we're going to look at that projection. First operation, union. Standard theoretic definition of union is given that A union B is a set X where X belongs to A or X belongs to B. For example, we have the set A B C union the other set A D E. We are going to combine all of them, but since the definition says or, means if there is an element present in the first set and that element is equally present in the second set, we are going to write it once in the final set. We see that A is present in the first set, A is present in the second set, but we'll write it only once. There's B here, there's C here, it is not there, we'll put it. There's D, there's E, we'll add it in the final set. This gives us A union B. The relations we want as a result of a relation, for relations we want a result to be a relation equal as we earlier defined above. So a set R, the set R, which is a subset of the Cartesian product of A1 to AN for some n and the domains are A1 to AN. Union compactable relation. Two relations R and S are union compactable if they have the same number of columns and the corresponding columns have the same domains. What are the conditions? We have what? The same number of columns and the corresponding columns have the same domains. Those are the two most important rules, so just keep in your head: the same number of columns and the same domains. Example, let us see if these two relations are union compatible. Look at the first relation. We have the first column which contains things like names, the second column which contains letters of the alphabet, the third column which contains digits. Now look at relation 2. The first column contains name, the second column contains things like year of birth. But when you compare the two relations, you observe that they are not union compatible because the first relation has 3 columns or is of degree 3, and the second relation has 2 columns or is of degree 2, so they are not union compatible. Let us look at this other example. The first column has a degree 2 columns. The first relation has a degree 2 columns. Second relation has a degree 2 columns. But now let's look at the content. For the first domain, they have names of birth, yes, but look at the second domain. It has a letters of alphabet and the other ones have year of birth. So you see that they are not union compatible because the contents of the domains are different. Now let's look at this other example. We see that it is we see that this one is union compatible because first, the two relations are of degree 2. The contents of both relations are similar. We have the first domain which contains name, the second domain which contains year of birth, so they are union compatible. Example, let's look at the union of two relations. Given this shopping list, a relation R and S, let us find R union S. We have in the relation R cheese with its price, which is 1.3, milk I don't know if it's quantity or price, but okay, look, but let's take quantity and measure in kilograms. Milk 0.8 kilograms, grams 0.6, no gram. Let's take grams. Eggs 1.2 grams, soap 1.0 grams here, and then we have relation 2, which is relation S, which we have cream 5, soap 1. Now we will now unite the two of them. From our definition of union, we say what R union S is the set X such that X belongs to R or X belongs to S. Meaning that if there is an item which belongs to each to any of these sets, we put them in the resulting set. We start with relation arrow. We take all the items of relation arrow and fit inside the result. We have cheese, milk, bread, egg, soap. Cheese, milk, bread, egg, soap. We come to relation S. We have cream, soap. Cream, soap is already there, so we just leave it there, right? Since soap is already found in relation R is equally found in relation S. Difference of two relations. Let R and S be two union compatible relations. That difference, R minus S, is the relation which contains the tuples that are in R but not in S. R difference S is a set X such that X belongs to R and X does not belong to S. Note that the difference is also a partial operational relation. When we talk of partial operational relation, it means that it's a type of it's an operation that works on relations, on certain relations, not on all relations. So it is partial. Example: what is the difference between the relation R and relation S? Now we are looking at items that are present in R that are not also items that are present in R and is present in S. We remove those items and then the result will be the difference, right? Now if you look at relation R, we'll see that there's an item soap which is present, and if we look at relation S, we see that soap is equally present. It means that in the final result is not going to have soap. Now let us perform it. We have what? Cheese, which is there, milk, which is there, bread, which is there, eggs, which is there, and cream. Is typing error, so cream is equally supposed to be there, right? Cream, and then the price is 5.0. Yes, so cream, yeah, you just add cream just below this the final relation. Intersection of two relations. Let R and S be two union compatible relations, then their intersection is a relation R intersection S, which contains tuples which are both in R and S. In R intersection S is the set X such that X belongs to R and X belongs to S. Please take note of this of the definition. The set X such that X belongs to R and X belongs to X. What is important here, you should note that it is it's an AND relation, meaning that for example, let's take this example. For example, if we have an item present in relation R and an item present in relation S, that item will give us the intersection. Now let us look in relation R. We have cheese, milk, bread, egg, soap. Relation S, we have cream, soap. The item that is common to both relations is soap. So the intersection between R and S will give us what? Soap. Cartesian product. We've used the Cartesian product to define what a relation is. Now let us define what a Cartesian product is. A Cartesian product is a total operation on relation. Usual set theoretical definition of Cartesian product is such that the Cartesian product of relation R and S is the set xy such that x belongs to R and y belongs to S. Under standard definition, if for example I have cheese 1.34 which belongs to the relation R, and soap 1.0 which belongs to relation S, then we say that the Cartesian product is cheese 1.3 comma soap 1.0 belonging to the relation R by S, belonging to the Cartesian product, which is give us the relation R by S. The result is equally a pair of tuples. So you should understand that once you perform the Cartesian product, it gives you another relation. Extended Cartesian product. Just look at this example above. We have two pairs separated by comma, but in an extended Cartesian product we are going to have just a single pair, right? Means that we'll combine the two pairs to form a single pair. The elements that separated cheese 1.34 and sub 1.34 will take it out and they will form to create just a single pair. We call that the extended Cartesian product. Henceforth we are going to be dealing just with the extended Cartesian product, so keep that in your mind. Extended Cartesian product of relation. Let R be a relation with column domains A1 to AN and S be a relation with column domains B1 to Bn. Then the extended Cartesian product R multiplied by S will give us a relation R by S such that C1 to Cn, Cn plus 1 to Cn plus m, such that C1 to Cn belongs to the relation R, Cn plus 1 to Cn plus m belongs to the relation S. For example, we have the relation R and S: cheese, milk, bread, egg, soap, cream, and soap. Let us perform the Cartesian product R by S. First, we'll take cheese, right? Or yeah, we can take cheese, right? Or we take cream. Yeah, it's like this. We take cream, and then we form pairs with each of the elements in R. Then we take soap, we form pairs with each of the elements in R. Now let's start with cream. Cream. We take, you see, cream 5.0, then element R, cheese 1.34, cream 5.0, milk 1.34, cream, bread, cream, eggs, cream, soap. Now we go now to the next. We take soap, soap, cheese, soap, milk, soap, bread, soap, egg, soap, soap. That gives us the Cartesian product of the entire relation. Projection. Let R be a relation with n columns and X is a set of column identifiers. At the moment we will use numbers, but later we are going to use names like email, telephone to describe the domains of various relations. Then projection of R on X is a new relation, pi subset X R, which is read as the production of R of columns X. For example, the projection of the relationship R of columns 1 and 2 is a table with only one of the second columns in R. Now let's look at this example. Given the relations, we have relation 1, relation 2, and relation 3. We are projecting columns 1 and 3. We see that the result will give us just columns 1 and column 3. You see, the first columns 1 contains names Anne, Bob, and Chris, and column 3 contains a set of a set of digits. That is, we just extract column 1, extract column 3, and produce a new relation out of it. We call that a projection of the relation R of columns 1 and 3. Selection. Let R be a relation with n columns and alpha is a property of the tuples. Selection of R subjects subject to condition alpha is defined as follows. We say that with the selection of R subject to condition alpha is given as a set A1 to AN, which belongs to the relationship R such that the condition is A1 to AN. Before we continue, it is important that we look what a reasonable property is. We can assume that properties are written using an or not, and expressions of the form call one the comparator column J, where I and J are column numbers. Now the comparator, this comparator can make sense if we apply it to values of I and J, and the comparator could be maybe equal to, not equal to, or maybe comparisons like less than or equal to, greater than or equal to, less than, greater than, if there is a natural order on the values. Meaningful comparison. We can always at least tell if two values in the same domain are equal or they are not equal. That is, that first the domains have to the content of the domain have to be similar, and then we can then now do a comparison. For example, if we have two domains containing years of birth, we could test if if a year of birth is greater than another year of birth. That is a meaningful comparison. But if the content of the domains are different, we cannot perform this kind of test on it, because the contents are different. We cannot say that a name is equal to a year of birth. That is not possible. Now, example of a selection. The reason why we're talking about comparison and selection is because we are going to use commands that combine the two together. Now, look at this example. Select column 3 less than 2002 and column 2 equal to none. So we come to column 3. This is 2002. If we are to perform the selection, you see that first we are going to select just that, eliminate the first tuple, right? We eliminate the first, we select just this, we eliminate the first tuple. Now let's say column 3 less than 2002. Yes, these are all the items less than 2002, and column 2 equal to null. Column 2 equal to null. Only this one has null, so the result will be what? Memento null 2000, right? So far we have looked at data. We have looked at data which is better on tables, operations on tables, union. We have looked at differences, intersection, extended Cartesian product, projection, and we also notice that the relation of each of them is equally a tuple. You have to do this example as your assignment, and please let me advise you, make sure you do all the assignments, because your exam will be a collection of these assignments. In next lecture we shall look more on relational data integrity. If you have any questions, you can just write it down on the chat group, or you put it on a WhatsApp group, and I'll comment on it at the earliest. Hello everyone, welcome to lecture 3, relational model. In this lecture we shall look at relational data integrity. Before go ahead, it is important for you it is important for us to remind ourselves that E.F. Cort in the 1970 proposed a relational model in his paper titled A Relational Model of Data for Large-Scale Data Banks. And this model which he proposed forms the foundation of our current database systems. And in that paper, he focused on three contributions: data structure, data integrity, and data manipulation. So let us start with the first one, data structure. Data is stored in relations in the form of tables, as we have earlier seen, and this is an example of a relation. And each of these relations has a scheme. The scheme is what we call the heading. The scheme is also a set of attributes, right? Where you combine all the attributes together, it forms the scheme. Now data takes the form of tuples. This is data. They take the form of tuples, mean they appear as rows in the table. Now, before, when we were defining relations, we labeled the various columns using numbers, right? We gave numbers as names of the attribute, but now we are actually using names or words that reflect the content of each of the columns. That is called, now when we're using numbers, it is called an unnamed tuple, right? But when we are using names that reflect the content of the column, it is called named tuples. An example of an unnamed tuple, remember we said that we could write the contents of the tuples as pairs of elements: John, 23, Mary, 20, just as simple as that. But in the case of a named tuple, you have to put the name of the attribute, comma, the content, you put them in parentheses, comma, then the attribute age, the content 23. Fundamentally, you have to understand that there is no big difference between name and unnamed tuple. It's just a matter of perspective. We could equally write the tuple ABC as 1A, 2B, 3C. Given that the columns were labeled as 1, 2, and 3, right? The attributes were 1, 2, and 3. Or we could simply just write 1, 2, and 3 because we know the order how the alphabet goes. Now, when we are writing sets of tuples, or when we are writing pairs of tuples, the order is not important, right? You see, we write maybe 3C, 2B, 1A in their pairs. It is not really important. More formally, a scheme is a set of attributes. Name H, that set is the scheme. A tuple assigns a value to each attribute in its scheme. A tuple, let's look at the tuple John 23. John is assigned to name, 23 is assigned to age. The same thing, Mary assigned to name, 20 is assigned to age. A relation is a set of tuples with the same scheme. Now, a set of tuples with the same scheme. These are a set of tuples. We have this, the first tuple, name John, age 23, name Mary, age 23. This you see that they have the same scheme, name, age, and the tuple is as assigned values to each of this scheme. So it means that this is a relation. For example, take a look at this relation. The very first tuple is the scheme, and it describes the contents of each of the columns. Now, we could also write the scheme as ID, name, salary, department. The attributes are the elements present in the scheme. So we have attributes ID, name, salary, and the department. Now the degree in this relation is 4, meaning is the length of the tuple, right? The number of columns present. So I have 1, 2, 3, 4, and the cardinality is the number of tuples present. We have 1, 2, 3, 4, 5. So the cardinality is 5. Data integrity. Data integrity controls what data can be in a relation. The domains restrict the possible values that a tuple can assign to each attribute. And candidate and primary key identifies tuples in a relation. Foreign keys link relations together. Now we are going to look at this a little bit detailedly as we go ahead. Now let us start with domains, attributes and domains. A domain is given for each attribute, and the domain lists the possible values that that attribute can contain. Each tuple will assign a value to that attribute from the domain. Now, example, an age might have to come from the set of integers between 0 and 150. A department might just be a given list of string. Notes might be any string at all, right? That's the domain. That means age is going to be a number or an integer that lies between 0 and 150. A department is just going to be a string. A string is a combination of characters. Note, on top of note, mean some sort of like lesson note or something. Yeah, note would be any string at all of maybe a very large length, so that it could really look like notes, right? Candidate keys. A set of attributes in relation is called a candidate key if and only if these are the two conditions that define what a candidate key is. The first condition is that what every tuple has a unique value for the set of attributes. The property of uniqueness, meaning every tuple is going to have a value that only it is going to have throughout in that entire relation. This next condition is no proper subset of the set has the uniqueness property. That's the property of minimality. Now let's look at this example. Take the relation on the right, where we have that has the attribute or the scheme id first last. Now the candidate key could be just the id. It works. Candidate key could be the first and last name. It looks plausible, but we might get people with the same name, so that is not a good candidate key. We will have the id and the first name, id and the last name, yes. id first and last name, they all satisfy the uniqueness property, but they are not minimal because we could have people with the same names. First and last do not give the unique identifier for each of the rows, so it cannot work. Choosing candidate keys. Now when you're choosing candidate key, it is important for you to note that it's not just to look at the data in the table and determine what kind of key you should give, but the table you should use knowledge of the real world in order to determine the type of key that you assign to a tuple or to a relation. Primary keys. Primary keys are very similar to candidate key. The only difference here is that the only difference here is that a candidate key is usually chosen to be used as a tuple in the relation, and that candidate key that is chosen to be used as a tuple in the relation is what we call the primary key. Now let us go back to our previous example. You remember in this example we came out with several candidate keys. We have id first last. Yeah, those are very two plausible candidate keys, but we have to choose one of this candidate key and then use it as identifier of that relation. If we choose id, for example, it's going to be used as the identity of that of the tuple in that relation, right? Because it is unique and it obeys the property of minimality. Nulls and primary keys. Now, any missing information in a database is represented as a null. A null generally indicates a missing or unknown value. We shall look more on this later. Now, primary keys cannot contain null values. A primary key cannot contain a null value. Foreign key. Foreign keys are used to link data into relation. A set of attributes in the first, that's the referencing relation, is a foreign key in its value, always in its value. Now, what does it mean? Example. Now, look at these two relations: department and employee. In department, it has two columns: DID, department ID, department name. In department ID, this is a candidate key, and if you choose it as the identifier of the tuples in this relation, it will become the primary key here. Employee table, the primary key here is EID. It's a candidate key, but if we choose it as the identifier of tuples in this relation, it becomes the primary key, right? Now, still on this table, one of the attributes is DID. DID is the primary key for the table department, but it is present in the table employee as a foreign key because it references the department name to the employee name. What does this mean? It means that John Smith, having the department ID 13, it will also imply that John Smith is belonging to the marketing department. Referential integrity. When relations are updated, the referential integrity could be violated. This means that when you update or edit a relation, you can change how the properties which it respects. And in order to avoid such violations, you have three options. We could restrict, cascade, or nullify updates. For example, take a look at these two relations. We have the department relation and the employee relation. If we modify the in department ID, if we modify 13 to 16 and we delete account, what will be the effect on employee table? Now, you see that it's going to cause some changes, right? It's going to really jeopardize the integrity of the entire relation. Now, to avoid that, we can do what we call restriction. Now, restriction stops any action that violates integrity. It means that you will not be able to perform updates, you will not be able to change this 13 to 16, and you will not be able to delete accounting or marketing. So you are just not able to do any changes once you've set up the table. Or better see, you could do cascade. Cascade allows changes to flow through. For example, if the marketing DID is changed to 16, right? If the marketing DID is changed to 16, we are going to come to its correspond to the table which it was referenced, where we have 13. We change the 13 there to 16. 13 to 16. If we delete accounts tuple, we'll come to the table. The ID for account tuple is 14, so we'll come to the ID for 14. We delete the tuple there too. That is what we call cascade. You make the changes to flow through. Nullify sets the values to null. If marketing DID changes, then John Smith and Mark DID would equally change to null. What does that mean? Now, if we change the DID for John, right? This is John Smith. We change his DID. Oh, excuse. Okay, now if we change, let's say we change marketing DID from 13 to 16, right? When we come to the DID, this is 13 here. We have changed it to 16. It simply replaces the 13 with null. There's 13 here equally. It simply replaces it with null. Next, if account is deleted, right, the ID for account is 14, we count to 14, we simply change it to null. That is what we call nullifying to solve the problem. Apparently now we can see that foreign keys can take null, but primary keys cannot take null. Naming convention. It is important that when naming your attribute, you give names that resemble the content of that of the column, right? A consistent naming convention will always help you to see your structure clean and clearly. It is advisable to assign a unique prefix so that so as to easily give names to the various attributes. For example, if we have a relation student, we will have attributes like student, stu name, stu department, something like stu module. Yeah. Having a unique number as a primary key is always useful, and if the table prefix is ABC, then we can call that unique number as primary key ABC ID. A foreign key in this table is then also called ABC ID. For example, we have this set of three relations: student, enrollment, and module. In student, the primary key is two IDs, two name. You see how the convention come. You take the first three letter of the relation and you put it as the prefix in front of all the names of the items in of the attributes of the scheme, all the in front of all of the items in the scheme. Enrollment. Enrollment is a relation that contains is made up of foreign keys only. It has two ID and mod ID, which are primary keys of relation student and module. Great. For the next lecture, we shall talk on entity relationship models.